when we left off. We've been spending a lot of time on hybridization and molecular shapes the last chapter, and it worked very, very well for the most part. But then we get to some problems, and one of the problems is that it doesn't always explain shapes, and as we'll see, it doesn't explain magnetism terribly well. So this was the new method of looking at bonding. And instead of looking at atomic orbitals, which then hybridize within the individual atoms so that then they fit together with other individual atoms, the idea is that the molecule itself forms new orbitals, bonding orbitals and anti-bonding orbitals. And the more electrons you can put into bonding orbitals, the stronger the bond is. The other thing I want to point out that's a lot different about this particular theory is that instead of just looking at individual bonds, right now we're looking at individual bonds, but when you look at entire molecules, what this theory does basically is take the molecule as a whole. And if we were to take all the atoms and all of their bonding electrons and put them together into all the valence electrons and put them together into a molecule, we would see that instead of just individual bonds being formed, that in a lot of instances, electrons are delocalized. And we sort of looked at that a little bit when we were dealing with making different molecules. We would put together our dot structures and then make bonds, and then we would see that sometimes there'd be a double bond and sometimes there'd be a single bond, and then sometimes we would want to move that bond around. Well, molecular orbital theory makes the observation that there's no such thing as a double bond on one side and a single bond on the other side. What you actually have are delocalized electrons moving around the molecule as a whole, leading to bond orders, like fractional bond orders, like we've seen before: 1 1/3, 1 1/4, 1 1/2, 2 1/2, that sort of thing. But the very basic part of the theory comes down to this. This is like the very simplest molecule we can form. Here we have just a couple of little old hydrogen atoms. And as we recall, they only have 1s orbitals. That's it. They can't hybridize. There's no place to put. There's no higher energy orbital space to put another electron. So they're stuck with just 1s. So what happens is when they get together, they form two different kinds of orbitals. One where there's bonding, so there is shared electron density between the two atoms. And then the other orbital would be what we would call anti-bonding, where the electron density, instead of being between the two atoms, is actually pushed away. And if you remember, that's what we were talking about. If you look at it as waves, the bonding is when the two waves add together and you get more electron density in between. And then the other is when the two waves sort of cancel each other out, and then you get nothing in between. Basically, you just get a blank. The two waves come together, they cancel each other out, and then there is no electron density in between. So either you get bonding, where there's density in between, anti-bonding, where that density is moved away from the two nuclei. And so we call the bonding orbital sigma, because it's a sigma bond. And this is the name of the atomic orbital that those electrons come from. So we just call it sigma 1s. When the anti-bonding orbital is formed, we put a star in front of that. That just means that electron density is moved away. Basically, we're subtracting this 1s and that 1s. We're subtracting them so that they move away from the nuclei. The bonding orbital is lower in energy. It's more stable. A hydrogen molecule is more stable than two hydrogen atoms because they've come together, they formed a bond, they're sharing a pair of electrons, and that adds to stability. When you formed a bond, you then achieve, if you remember going way back, you try to achieve the electron configuration of the nearest noble gas, right? I mean, that's what you're looking to do. That's what the atomic orbital theory told us, was that all the elements were trying to get to a stable electron configuration. Well, this is basically the same thing. This is just adding to that a little bit. And it gets to that stable configuration with its two electrons. So now it's similar to helium. So it's in addition to all the theories we've learned so far. It doesn't completely replace them, but it's sort of an addition. It's a different way of looking at it. So then we learned that there's going to be a molecular orbital diagram, just like there was an atomic orbital diagram, S, P, D, and F. And the molecular orbital diagram shows where the electrons come from, which atomic orbital do those bonding electrons come from, and then where do they go? And then we figure out what the bond order was by seeing how many electrons are bonding. Let's say we have 8 electrons in bonding orbitals. We have 4 electrons in star or anti-bonding orbitals. What's the bond order? We divide that by 2. The reason why we would divide that by 2 is because we're counting electrons here. Remember, these are electrons. And how many electrons are there in a bond? What have we learned so far? How many electrons make up a bond?
2.
Exactly. And so we're saying the same thing here. The relative density of 2 electrons, not 1, but 2, counts as a bond. And so the bond order here would be 8 bonding electrons minus 4 anti-bonding electrons divided by 2 equals 2. So that would be the equivalent of a double bond between those 2 atoms. Bond order is 2. Now, we don't really think of it so much as a sigma and a pi. In this particular instance, we just think of it as a bond order of 2 because remember, we're sort of sharing electrons, not so much in the same kind of space that we're used to thinking about, but just basically the electron density between those 2 atoms is equivalent to 2 bonds. And that's really all we have to think about. We can still think about the first one being sigma-like and the second one being pi-like. We don't have to shy away from that. So this is the simplest molecular orbital diagram that we've seen so far. Now this is how we draw them. We have atomic orbital for the first atom on the left. So in this instance, we have hydrogen on the left and we have a hydrogen on the right. Those are the 2 atoms that are coming together to form our molecule. Each of them brings a single electron to the table in a 1s orbital. So when we add them together, we get overlap, we get a bonding orbital, we get more stability, we get a sigma bond, the sigma bonding orbital. The other addition, if there are any more electrons, which there aren't here, but there may be, if there's any more electrons, we would then put them into the sigma star, anti-bonding. But here, very simplest model, we have 1, 2 electrons in bonding orbitals, and we have nothing in the anti-bonding. 2 minus 0 is 2, divided by 2 is 1. So our bond order is 1, which that's obvious here. It's a single bond. It's only 2 electrons, actually. We can't have any more than that. It gets a little more complicated when we introduce the p atomic orbitals. Now, if you remember, the p atomic orbitals are in that x, y, and z direction. So x goes from side to side, y goes up and down, and z goes in and out. Wait, there it is, in and out. So x is the line between the 2 atoms. So here's my 2 atoms. Let's say I got 2 carbon atoms here. So its p orbitals in the x direction would overlap because they're directly come in contact with each other. These overlap. These can form a sigma bond. And so when we add them together, we get extra overlap between the 2 atoms. And when we subtract them, we push away that electron density, again, away from the 2 nuclei, the 2 carbon nuclei. So in this instance, we have sigma bonding of the p orbitals because they directly come in contact with each other. On the other hand, we have these 2 orbitals, the y, that look like pi bonding, like we're sort of familiar with. Remember, we have, if these are my 2 carbon atoms, and this is my sigma bond in between, remember we have electron density both above the single bond and below the sigma bond. So when we add those together, we get this familiar shape, the good old hot dog bun of pi bonding, where we have electron density above the single bond here. We have electron density below the single bond there. So if you remember, with sigma bonding, you have electron density directly in between. That's a strong bond because it's right there. It's right between the 2 atoms. It's more dense. The electron density is higher between the 2 atoms. With a pi orbital, the electron density is a bit more diffuse. As you can see, it's much bigger, and it's split in 2, so it's both above and below. That is not as strong, and it's still true with this theory. Sigma bonds are still stronger than pi bonds. So that's what pi orbitals look like when you add them. When you subtract them, you get this. Basically, you sort of push the 2 lobes. So if my 2 lobes of my p orbital are like this, basically when I push them away, basically squeeze them away from the other atom. So the direction is pushed away. And so here, again, I get my addition. When I add the 2 waves together, I get my addition. And when I subtract them, I get nothing in between. So it's a weird looking orbital, but I think it sort of makes sense that you're instead of adding them together so that they come together, you're pushing them apart. It's almost like that they're repelling each other. And that's what a sort of pi antibonding orbital would look like. So we add all that stuff together. What do we get? So now we get sigma and pi, bonding, anti-bonding. Sigma is always going to be more stable, so lower energy. Pi is going to be higher. One thing I don't want you to worry about too much is this mixing thing. Sort of mentioned the last class, that the difference in energy between 2s and 2p gets pretty small when there's not much, when the nucleus isn't pulling on them very much. They tend to sort of just, the energy difference tends to drift to like less. It gets less and less. When the nucleus is pulling on them very tightly, then the energy difference gets more and you don't get mixing. So that's why when you have boron, carbon, and nitrogen, they mix together. But then when you start to get oxygen and fluorine and neon, they pull on the electrons much more, and then you don't get mixing. Don't worry about this too much. What I will do on tests is I will give you this. So I'll set that up for you. This will be the order that you fill in the electrons, and then it's up to you to figure out where they go. The same rules are going to apply. When we fill up our atomic orbitals, we go to the lowest. Who's the lowest energy? Oh, S. So I put my electrons in S, and then P is next, and I go 1, 2, 3, and then I come back 4, 5, 6. Same is true for these molecular orbitals. I would start with sigma 2s. I would go 1, 2, and then I move up to the sigma star 2s. 1, 2, and then sigma 2p. Okay, 1, 2, and then when you get to the pi and pi star 2p, notice that those are degenerate orbitals, degenerate meaning equal energy, just like p orbitals are. But instead of 3 of them, there's only 2. So what we would do in that situation, now that we have pi and pi star, either one, we go 1, 2, 3, 4. We follow the exact same rules we did before. And that'll be really important for figuring out magnetism, figuring out the right number of bonding and anti-bonding electrons. We just follow the same rules we did before. So here is where they flip. The only difference is the relative energy between pi and sigma. That's it. That's the only difference. So the difference in the sigma and pi stars don't really change. It's just the bonding energy. It's just slightly different. But again, don't worry too much about it. I will give you, when I give you the different elements that I want you to construct a bond from, I will fill in the proper levels of molecular orbitals for you. You need to figure out where the electrons go. And as I mentioned earlier, probably mentioned a lot of this earlier, I tend to repeat myself. One of the reasons why the molecular orbital theory was developed was because oxygen had been known for a long time to be magnetic. This is a picture of liquid oxygen being poured over a magnet. And I don't know if I'm completely convinced by this picture, but it's being drawn towards one pole and repelled from the other. Of course, it will look like that if you just pour it on one pole and not the other, but there you go. But take my word for it, it is paramagnetic, meaning it is attracted to one pole. And so let's look at what we've learned about oxygen. So if we're going to draw oxygen, how many valence electrons in oxygen? So I'm going to do my Lewis dot structure of oxygen, try and figure it out. Maybe 6. No, halfly, yes, 6. So there's a total of how many electrons in this structure? Everyone's so quiet. You want me to do all the yakking? Yeah, a total of 12 electrons. So I got 2 in that bond. So I got 10 electrons. So I go 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So that's not going to work, right? Because neither oxygen has the right number, has an octet. So what do I do? How do I get around that? Right. We then would just take this oxygen would donate an electron to the middle. This oxygen donates an electron to the middle. I form a double bond. And so, as I've been sort of, yakking about forever, oxygen will almost always have this particular look to it. 2 bonds, 2 lone pairs. That's the easiest way for oxygen with 6 electrons to get an octet. 2 lone pairs and 2 bonds, because the 2 bonds give you 4. The 2 lone pairs give you 4. Everybody's happy. So according to this model, what's the hybridization of the oxygen? Because now we want to look at it with hybrid orbitals. What's the hybridization of the oxygen atoms? Aaron coming through. sp2. Whoops, damn it. Yes, sp2. Because there's 3 regions of electron density. So we need 3 places to put electrons. And so we take the S and the P, and we put electrons there. And then we have another P here. So we go 1, 2, 3, 4, 5, and then we have 6. So this would be our sp2 orbital, and that would be our p orbital. Who makes the sigma bond? So remember, we have a sigma bond and we have a pi bond. Which of these orbitals, sp2 or p, makes the sigma bond? P for pi. Which one makes, so P makes the pi. P makes the pi bond. That is true. So if I have oxygen 1 and oxygen, I'm going to use different colors here. Oxygen 2. So I've got my oxygen 1, my oxygen 2. Each of them are sp2 hybridized. So they each look the same. And then there's oxygen 2's sp2, there's its unhybridized p orbital. So which electrons, so these 2 electrons make the pi bond, right? This one and this one. So they would overlap, and so we would have a p orbital with we have a pi orbital with 1, 2 electrons in it. So they would come together. With the sp2, the 2 sp2 hybrid orbitals, what would they make? Which bond do they make? They make the sigma, right? So basically this electron and this electron go into an sp2 orbital, 1, 2. That's your sigma. That's your sigma bond. That's your pi bond. This pair of this lone pair, that one and that one and that one stay in their own sp2 orbitals. Now, are there any electrons that are alone? Are there any unpaired electrons in this particular setup? Do we have any unpaired electrons? No, we don't. We don't have any unpaired electrons. The 2 p electrons come together, form a pi orbital. One spinning up, one spinning down. The 2 sp2 lone electrons come together in an sp2 overlap. They overlap, one spins up, one spins down. So according to the hybrid orbital theory, all of these electrons are paired. They're all paired together, one spinning up, one spinning down. What would that predict as our, would that be a diamagnetic or a paramagnetic situation? If all of my electrons are paired, their spins are all paired. Does that make it diamagnetic, where there's no attraction to an electric magnetic field, or paramagnetic, where there is an attraction?
Diamagnetic?
Exactly. It's diamagnetic. This predicts that that oxygen is diamagnetic because all of its electrons are paired. They're either in bonds, and when they're in bonds, they're, by definition, they're paired, or they're in lone pairs. Those are paired. So all the electrons are paired. But we know oxygen isn't diamagnetic. So what does that say for the magnetism? This is how it's explained with using molecular orbitals. So in this instance, we have, this is taken right from your textbook, we have 6 valence electrons. So we know there's 6, 2, 4, 5, 6, each one, right? So we have an oxygen on this side, we have an oxygen on that side. And we just start putting them together. Now we have a total of 12, and we start putting them together. 2, 4. So those are the lowest energies. We put 2 and then another 2. 6 means we have 6 left. And then for the next 6, we go 1, 2, 3, 4. And we have 2 left. 1, 2. Because remember, the pi, both bonding and anti-bonding, are both degenerate. They're both equal energies. And so we add it to one and then the other. And so according to this, what would be our bond order according to this diagram? How many electrons do we have in bonding orbitals? So we got bonding, 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 bonding. So that's 8. And then we've got anti, 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 4. So it correctly predicts that we would have a double bond between these two atoms. The other thing it predicts is that we have 1, 2 electrons in adjacent orbitals in terms of energy anyway, that are unpaired. These are 2 unpaired electrons. And remember, when you fill in your orbitals, you always start with spin up first, and then you put the spin down in second. So I have 1 orbital here, I have 1 orbital here, each with a single electron in it, each spinning in the same direction. Now, does that give us paramagnetic or diamagnetic? Well, kind of a dead giveaway here, isn't it? Because we have those two those 2 spins, we call those spin dipoles, just like electrical dipoles. When we have more electron density on one side than the other, that's a dipole. When we have spinning in one direction, not coupled with another, that's also a dipole. That's a spin dipole or a magnetic dipole. And so we have 2 magnetic dipoles that add together, so that basically that would be a spin dipole pointing up. That's a magnetic molecule. So that's would be the prediction for oxygen. Any questions about how we organize this? Or do we remember how magnetism is calculated? Man, this tea is supposed to make me not cough. It's starting to make me cough. Excuse me. Maybe it needs to be hotter. So Everyone's then familiar with the spin, the relationship between spin and magnetism. Okay. So let's go through. This is also from that might be from the previous textbook. I'm not sure how well you can see these. Just take my word for it that these dark, oops, let me go back, that these dark blue are paired and that the light blue are unpaired. Okay, that's like really the only difference. And so what we're doing is just going across the periodic table, seeing what kind of bonds we would form if we took the two atoms and joined them together, what kind of bond we would form, what the order is, whether it's not it's magnetic, and how close the atoms would get. So here we have boron. Can you put two borons together? So we put them together, bonding, anti-bonding, bonding. Yes, that would work. We would get a bond order of 1, and since we have 2 electrons that are unpaired, we would get a paramagnetic molecule, and that is the case. Then we move over. Now we have carbon. With that, will we get bonding in that situation? Yes. Bonding, 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 anti-bonding. This time we would get a double bond, and it would be diamagnetic because there are no unpaired electrons. Move over a little bit more. We know we form N2. We've been drawing that for quite a while now. This time we have 1, 2, 3, 4 sets of electrons, 8 in bonding electrons, and still only 2 in anti-bonding. That would give us a triple bond, and we know that that's true also. And it's also diamagnetic. It's not magnetic either. And then finally we go to oxygen, which we just did. That gives us a double bond that's paramagnetic. Fluorine, when we get to fluorine, all of our electrons are paired up, and we have 1, 2, 3, 4 pairs of electrons in bonding orbitals, and 1, 2, 3 pairs of electrons in anti-bonding orbitals. That gives us a bond order of 1, which is true. So you can see the more bonds you get, this orange graph shows you how much more energy that bond has. So single bonds, obviously, for lower energy, and then double, and then triple, we get more and more. The other thing we notice is that the bond length gets shorter. So with a single bond, the 2 atoms are this far away. A double, they get a little bit closer. A triple, they get even closer because the atoms need to get close enough to each other for those orbitals to overlap and form. And so they need to be close. So they get pulled closer and closer together. And notice that when we get to neon up here, we have exactly the same number of electrons in bonding orbitals as we have in anti-bonding orbitals. And so we would predict no bond would form. And that's also the case. So any questions about this table? Basically shows you as we add more electrons, when we put them into bonding orbitals, we get stronger bonds. When we put them into anti-bonding orbitals, we get fewer bonds and they're weaker as well. And then finally, when we have equal numbers of bonding and anti-bonding, we get nothing. And that's what happens when we get to the noble gases. Any questions? Just going to keep on going. All righty. I swear I got some questions for you guys coming up. So we'll do this one together. So we want to explain this following data we're looking at. So these are a couple of molecules you'll be familiar with. Oops. Nitrogen and oxygen. So we're familiar with those. Triple bond between the nitrogens, double bond between the oxygens. What about if you take an electron away? What does that do to the the bond energy, the bond strength? Well, look what happens. When we take an electron away from nitrogen, the bond energy goes down and the bond length increases. That sort of tells us that we're weakening that bond. We're taking a triple bond and we're making the bond order less. But look what happens with oxygen. We take an electron away from oxygen, the bond energy goes up and the bond length goes down, indicating that we're increasing the attraction between the two oxygens. They come together even closer and the bond is even tighter than it was before. That's weird to think about, right? So with one, we're decreasing the bond order. With the other, we're increasing it. So if we were to prove that, how would we go about doing it? So it shows you that removing an electron seems to have an opposite effect. It makes nitrogen less stable, it makes oxygen more stable. So then we're going to calculate bond orders. So let's do that. So nitrogen, let's just go ahead and put our electrons in for nitrogen. So with nitrogen, how many total electrons are we going to have with N2? Total valence electrons. I have 2 nitrogen atoms. How many total valence electrons do I have? Not 7. Not 14. 10. Right, we have 10. Each nitrogen in group 5 has been for a long time. Nitrogen in group 5. So if I have 2 of them, I got 10. So I have a total of 10 electrons. So where am I going to start putting them? Where's the first place to put them? Sigma 2s, right? 1, 2, and then 1, 2, 1, 2. So that's 6. So I have 4 more to go. So where do I put them? And in what order? That's kind of important. 10 electrons. So where do I put the next electron? I'll put the first one here. Where does the next one go? 1 in each, right. 1 in each. So I have 6, 7, 8, 9, 10. So now I'm out. So what's the bond order here? How many electrons do I have in bonding orbitals? How many electrons do I have in bonding orbitals here? 8, right. 2, 4, 6, 8. Right, so I have 8. And then how many do I have in non-bonding? Or not non-bonding, sorry. But want to get that confused. Anti-bonding. 2 in anti-bonding, right, these 2. So my bond order is 3. Now, let's take one of those electrons away, because in N2 plus, how many electrons should I have total in that molecule? Right, I should have 9. 9 means that I now have a net positive charge of 1. So I should have 9 electrons there. So basically, it's the same thing. I'll just put in my electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's my 9. Now how many electrons do I have in bonding orbitals? 7. Right. Now I've got 7. 2, 3, 5, 7. So 7 minus 2 divided by 2 is 2.5. So you see that my bond order is decreased by a half. So instead of sharing an even number of electrons, I'm sharing an odd number of electrons. And so I'm sharing one less. So my bond order goes down 1. That would lead to the bond energy being less because it's not as close, it's not as tight as it was before. And the length would decrease slightly because they're not held together as closely as they were. So they would move apart a little bit. So that would explain that. So let's do, so our bond order here was 3, and this was 2.5. Let's do oxygen now. Total number of valence electrons in an O2 molecule. 12, right, Ferris, 12. So let's put them in. So 12 electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So how many do I have in bonding orbitals? Yeah, Mavla, I've got 8. So I got 2, 4, 6, 8. Right, so I've got 8 minus, how many are in anti-bonding? I mean, we just did this a minute ago. 4, right, Ariana, 4. These 2, 3, 4. Divided by 2. So my bond order is now 2. How many electrons will be in O2 plus? $11, right, so I take 1 away. And the one I'm going to take away is this one. That goes away. It's the highest energy electron. That one gets removed. So now, how many electrons do I have in bonding? Same number, right? Because I removed an electron from an anti-bonding orbital. So I have the same number of bonding electrons. I've got 8. Oops. I have 8. How many electrons in anti-bonding orbitals do I have? 3, right. I used to have 4, now I have only 3. Divide that by 2, and I also get 2.5. So notice, in each instance, I've gone from an even bond order to an odd bond order. But in one, I reduced the number of electrons that were in bonding electrons. But with oxygen, I've reduced the number of electrons that were in anti-bonding orbitals. And so I've increased my bond order. And that was represented in the actual experimental data. The 2 oxygens were closer together and the bond was stronger. And that shows up here using molecular orbital theory. So here's the actual representation. And yeah, you can see that works out. So here's our solution. So N2 has a longer, weaker bond because we've decreased the bond order because a bonding electron was removed. With O2, an anti-bonding electron was removed. And you can see the difference. I mean, you can clearly see the difference. You remove a bonding electron, it gets less stable. You remove an anti-bonding electron, it gets more stable, okay? So does everyone understands, everyone sees how that works, hopefully? Now again, I will give you the order of how you fill these in. And then basically it's up to you to figure out where they go. But you should be able to figure out things like this, like to calculate the bond order, see whether something is more or less stable depending on the bond order, and whether or not that molecule is going to be magnetic or not. Okay. Then I sort of want to show something we haven't dealt with: non-bonding molecular orbitals. Now, these are going to be different from anti-bonding. So what we're dealing with here is something where we have just hydrogen with this little 1s orbital, and we have fluorine, and its bonding electron is in a 2p. So remember what I said before, that p will overlap with another p or with an s. Remember, because we have p goes like that in the x direction. So here's my fluorine. It's got a p electron out here. I've got my hydrogen with its 1s with its electron there. They will overlap and form a sigma bond. And so I have sigma and I have sigma star. The other electrons, the other p electrons in this instance, aren't involved in bonding. They don't do anything. So we don't include them because they're not bonding, they're not anti-bonding, they're only next to fluorine. So that's it. That's the only thing they're doing, is they're being held close to fluorine as lone pairs. So they really have no inclusion with bonding in this particular sense. So you can see it looks a little different, but it's just because we just have a single electron interacting with a single electron, and it is just asking, where are those single electrons? With hydrogen, it's in 1s. With fluorine, it's in 2p. And so your diagram would look like this. Making the point again, these are not anti-bonding electrons. These are non-bonding electrons, meaning they do not contribute to bonding because those are fluorine's electrons. They're not included with bonding. Hydrogen doesn't get to share in them. Fluorine is very greedy, as we've seen many, many times. It's extremely good at pulling electrons toward itself. So those non-bonding orbitals, those are non-bonding orbitals. Hydrogen ain't coming close to it. So we don't include them in the diagram. So then one last thing, or a couple things just before we leave chapter 5 forever. I want to introduce a way of looking at nitric oxide. So help me do the diagram for nitric oxide. So I've got nitrogen, I've got an oxygen at a single bond. So how many valence electrons for nitrogen? 5. Yes. Hopefully, Ferris, that was a new comment, right? 5 electrons. Okay, good. Yeah, so we have 5 here, and oxygen has how many? 6. So we see we're going to have an issue here, right? Because remember, whenever I say there's an odd number of electrons, it's going to be some weirdness. When an atom has an odd number of electrons, what do we call that? Radical, right? Radical. So we're going to have a radical here as well, because not all the electrons are going to be paired. So we have a total of 11 electrons. We've got 2 in this bond, so that's 9. So we'll go 1, 2, 3, 4, 5, 6, 7, 8, 9. So obviously we don't have enough electrons for everybody. Poor old nitrogen's only got 6. So what do we do with that? We want to, nitrogen and oxygen both want a full octet. So how do we go about doing that? Oxygen likes double bonds, nitrogen likes double bonds too. So put those in the middle. But now nitrogen's got 8, oxygen's only got 2, 4, 6, 7. So what do we do about that? So if nitrogen has 8 electrons, oops. So in this instance, nitrogen has 8 electrons, oxygen's only got 7. So what are we going to do? We need some way to get them both happy. Yeah, I can share an electron. That's right. I can take this electron and basically share it between them so that they each get to have it. So I'll take that one away and put it up here. So now each of them can sort of say they have 8, right? Each of them can say they have 8. And they're sharing, how many electrons are they sharing? What's the total number of electrons they're sharing in this situation? Five. That's right. They're sharing 5 electrons. 2, 4, 5. What's the bond order here? Two and a half. Exactly. So this would be stronger than a double bond, not quite as strong as a triple. We can't form a triple bond here because nitrogen can't violate the octet rule. Neither can oxygen. So we can't do that. So what happens is that they share a single electron rather than 2. And so we get something that's stronger than a double, not quite as strong as a triple, with a bond order of 2.5. So what would that look like if we do the molecular orbitals? Well, here we've got nitrogen with its 5, oxygen with its 6. We put them together. 2, 4, 6, 8 electrons are in bonding orbitals. 2, 3 electrons are in anti-bonding orbitals. Divided by 2, and our bond order is 2.5. So you can see that it does do a good job explaining magnetism and bond order in a way that we sort of didn't quite have with just the hybrid orbitals or the atomic orbitals by themselves. Okay? And then lastly, I sort of just wanted to make the point that what the really good thing molecular orbital theory does is show you when electrons are distributed around an entire molecule. Now here's benzene over here. Benzene looks like this. 1, 2, 3, and then each one has a hydrogen. Now, as you can see from this, it'd be really easy to just move this double bond there, and this one would go there, this one would go there, and then they just keep moving and moving and moving and moving. So basically what we have is a hybrid situation where there isn't a double bond between two carbons. So each one of these corners is a carbon. I should probably make that clear. Each one of those corners is a carbon. We just don't write it. In organic chemistry, you don't bother writing the carbon there. So like this would be carbon, carbon, carbon. Here's a double bond. Here's a single. So it would be really easy to put, like, there's a double bond between this carbon and there's a single between the next one, then a double and a single. Well, that's not true, because each one of those bonds, each one of those carbon-carbon bonds is exactly the same. They're exactly the same length and they're exactly the same strength. So therefore, the bond order between each one of them is precisely 1.5. And the way that that is shown is that you have basically this ring of shared electrons on top and a ring of shared electrons on the bottom that are basically moving around the entire molecule. So I have electron density equivalent to, we have 6 carbons, 3 electrons up here, 3 electrons down there. Sort of just, that's the density, each one. Same with ozone. Remember, ozone was also a hybrid situation where we had one oxygen was positive and one oxygen was negative, and you could move either one back. Either the one on the end would be positive, the one in the middle would be negative, and the electron basically turned out that we just shared an electron all the way around. And that's what the molecular orbital theory shows you, that there's in the pi orbitals, there's basically an electron shared around the entire molecule, not just one atom, the entire molecule. And so we have electron density above, electron density below, which is completely surrounding the whole molecule, not just one atom or 2 atoms. And that agrees with the sort of behavior we see from each of those molecules. It does a better job of explaining their physical properties than the hybrid model does. So before we leave this chapter, do we have any questions about the chapter? Because next we're going to go to chapter 6. So that's basically it for chapter 5. So if you have any questions about that, send them in to me. See me during office hours, or ask during class. That's always nice too. Okay. Anyway, so chapter 6. Oh boy. So as you can see, if some people have read ahead, and I'm sure everyone has, we have done a lot of this already. And so I may go through this slightly more quickly than I would, because we've been looking at solutions. We've been doing a lot of solution chemistry so far. We're doing titrations. In fact, this afternoon we'll do titrations again in my group with a little spin on it this time. Calculating molarity, calculating balancing reactions, all that sort of stuff we've been doing so far. So this will be sort of like a nice review. So hopefully we know how to balance a chemical equation at this point. So you get a statement: magnesium metal and oxygen gas react and give you magnesium oxide. So we know what magnesium is. It's a metal, so therefore it's just by itself, Mg. Oxygen gas, we know that's a molecule, that's O2. And hopefully we know by now how to balance this particular compound. Because what's the charge on magnesium? What group is magnesium in? When you look at the periodic table, what group is magnesium in? Group dose, yes. So when it forms, when it reacts with a nonmetal, it's going to lose its electrons because metals love losing electrons and nonmetals love taking them. This is an ionic compound. It melts at a very high temperature. So magnesium becomes +2. Oxygen group 6, it steals those 2 electrons. That's why we call it oxidation after all, because it's usually oxygen stealing them electrons. It's -2, and it balances MgO, magnesium oxide. Now, this isn't a balanced reaction because we have O2 on one side and the reactant side, and we have just a single oxygen on the product side. And we can't change the formulas, we just have to change the coefficients. So that means we have 2 moles, remember, of magnesium, and we get 2 moles of product. And it's important that we include the states of matter. In the last test, a lot of you forgot to include the states of matter. Metal's a solid, oxygen's a gas, and the oxide is going to be also a solid, unless this takes place in solution. And it doesn't in this particular instance because it says magnesium, not magnesium ion. So here, I'm going to let you guys do this one. And let's see if I can, I'm going to put a poll out there. There you go. What are the coefficients of this particular reaction? So you should recognize this is a combustion reaction. We have a hydrocarbon here. Now it's it's a big enough hydrocarbon that now it becomes a solid. I should have checked that. I think that's a solid. Oxygen is still a gas. And these are our 2 products, as we know. We get water and we get CO2. So balance the atoms, adjust the coefficients, make sure they balance, go ahead and solve it. Is everyone seeing the question? Can you see the question in the poll? Can everyone see it?
Yes.
Okay, good. So yeah, just take a little time. So what the question is, the coefficients. So the first one is for the hydrocarbon. Second one is oxygen. Third one is water. Fourth one is CO2. So basically A, B, C, D. You don't have to listen to me rave for a while. And no one's answered yet. I should have like a prize or something. Right, next week I'll have prizes. Man, is anyone doing it, or is everyone just staring at the screen? Everyone just staring at the screen. Someone's got to figure it out. Unless I mean, I could have made a mistake. Maybe these are all wrong. That would be bad. Come on, people. I've only got one vote in so far. I want at least half the class.
Professor, we can't submit the poll because there are several questions involved.
Oh, that's a problem. Okay, what I will do is I will fix this. I'll make individual polls. Yeah, I didn't realize how it works. So, I mean, one person voted, the rest of you can't, or you have to answer every question. Is that the problem?
You just put random answers.
Oh, that sucks. All right, so what I'll do is I'll stop this, and we can go back to it next week. I just want to show you the answers. Okay, so we'll do that. We'll do that next week. I'll fix that. So limiting reactant, we're sort of familiar with the limiting reactant. We've done this before. So we know that when you have two reactants, basically, if they're not balanced completely, that you're going to use up one before you use up the other. Now, the one that gets used up completely limits the amount of stuff you make. That's all it means. It means that, like, basically, like if you burning gas in your car, there's an unlimited amount of O2 in the atmosphere compared to the amount of oxygen in the tank of your car. So you're going to run out of gas before you run out of oxygen. That's the limiting reactant. So, and then you can't make any more CO2 or water vapor out of your tailpipe until you fill up again. It is limiting. So the reaction stops when you've used that all up. And then there's going to be some excess of the other one left over. So the question you will see next week is this one. And so people are asking me about rocketry and explosions and all that kind of cool stuff. This was one of the very earliest, I think Goddard, if you're familiar with rocketry at all, Goddard was one of the early inventors in this field. And just used this incredibly dangerous mixture of hydrazine, which is still used as a rocket fuel, and dinitrogen tetroxide, which is incredibly dangerous stuff. Why these are so good for rocketry is that when you want an explosion or you want something or in rocketry in particular, what you want are gaseous products, right? Because if you release a lot of gaseous products, it gives you a lot of thrust. Well, look at these two. The only products that form nitrogen and water vapor. So you get a lot of gases formed. But when they come into contact with it, you don't even have to have a match or a fuse or anything. The minute they come into contact, they explode. So very, very careful with that. So what you would need to do in order to do this reaction, obviously, is figure out, here's my hydrazine, here's my dinitrogen tetroxide, and here's my products. You'd have to balance the equation. That's essential, of course. Then, what's the next thing you would have to do? Once you've balanced the equation, what's the next thing you have to do?
Do we need to put the states of matter?
Not yet. I mean, yeah. I mean, if because that's actually not part of the question. But yeah, it'd be nice if you did that. I mean, these are all gases. So, or actually liquids. This is a liquid, this is a liquid, and then these two are gases. So yeah, we can do that. But what do we need to figure out before we can figure out amounts of product and amounts of reactant?
How many moles of each we have?
Exactly. Yeah, we got to go back. We got to go back. You thought you were getting rid of moles? No, it never goes away. So yeah, we need to, first we need to balance the reaction. Next, we need to figure out how many moles of each one we have. So we have 100 grams of hydrazine. We have 200 grams of dinitrogen tetroxide. We'd have to figure out which one is in excess. And how do we do that? How do we figure out which one is in excess? How do we determine which one is the limiting reactant? What does the limiting reactant do? What does it determine?
Is it the one that runs out first?
Right. How do we know which one runs out first, though? How do we know that? What calculation will we do to show us which one is the limiting reactant? You're absolutely right. It's the one that runs out first. But how do we calculate that? Good old stoich. Yes. What does that mean, good old stoich? We use stoichiometry, absolutely right. But what's the calculation we actually do in order to determine whether hydrazine or dinitrogen tetroxide is the limiting reactant?
We have to convert both to moles and then use that mole with the ratio from the chemical equation
Mm-hmm.
and just see which one runs out of moles, has less moles, or like runs out first.
But how do we do that? I mean, we actually need to calculate something that shows us, because it's not just the one that has the less moles. Remember, that is not the limiting reactant. It is sometimes, but it isn't all the time. I could have, fewer moles of one and more moles of the other, and this could still be the limiting reactant. What calculation do I do to show me which one is the limiting reactant? There's a calculation I can do and point to a number and say, you are limiting and you are in excess. What is that calculation? I mean, you're right. Everyone's correct, but everyone's sort of going around in a circle. I need to have a number. I need to point to a number. This number tells me which is limiting and which isn't. Yeah, and it's not a ratio. It's nothing like that. It's a number. I could point to a number like 11.6 versus 9.4. Two numbers I can look at, and it tells me which one is limiting. I guess it's good we're reviewing this. Lower number of what is the limiting reactant, Gabrielle? You're right. Lower number of something. Lower number of what? There you go. Yeah, look at the amount of product. And it doesn't even have to be the number of grams, Ryan. You can just, number of moles is fine. Because you want to see which one produces less product. That is the definition of a limiting reactant. If I have two reactants, in this instance, if I have hydrazine, remember I've got my hydrazine and I've got my dinitrogen tetroxide. They're going to make stuff. When they come in contact, they explode and they make stuff. The two things they make are nitrogen gas and water vapor. So you can pick either one. You can pick either nitrogen or water vapor as a product. Which one makes less? If I convert all my hydrazine to nitrogen, how much nitrogen is that? If I convert all my dinitrogen tetroxide to nitrogen product, how much does that make? Whichever one makes less, that's your limiting reactant. And it could be the second one, it could be the first one. I don't know, I just picked one. That tells you if it makes less stuff, that's the limiting reactant. Okay? And then to figure out how many you have left over, you figure out, okay, my limiting reactant tells me I'm going to make like 0.15 moles of nitrogen. That's all I'm going to make. If I make 1.15 moles of nitrogen, how much of my excess reactant did I use to make that? We use our molar ratios there. And then if I use that much, how much do I have left of the original? So we'll come back to this next week. I will figure out how to do the polling better. It was my first try at it, so it was bound to fail. Anyway, so I will leave it there, and we'll pick it up. I'll put the polls back in, and I'll have fabulous prizes. There'll be cars and boats and vaccines and all the stuff that we need to make our lives complete. So any questions before we go? So you don't need to convert, you don't need to figure out the grams of product here. All you need to figure out is what's the fewer number of moles of product. That gives you one less calculation to do. So it's not necessary. You will need to figure out the number of grams of reactant, but product isn't strictly necessary.
So in this case, would the product be N2 when we're comparing?
Either one. It doesn't matter. You can pick either one. Because if there's two products, they're each going to stop when the excess reactant runs out. So you're going to stop making nitrogen and you're going to stop making water. Because the water comes from, the hydrogen comes from one reactant, the oxygen comes from the other. So once you run out of one, you stop making both of them. So it really doesn't matter which one you pick. If it was just a single product, then that would be easy. But if you have two products, just pick either one. It doesn't matter. Because they'll both stop. Yeah. Good question. All right. I will see you, some of you, on Monday for office hours or next Tuesday. Have a good weekend. For my students, I will see you at 1:10, and we will do yet another, I know it sounds tedious, another weak acid titration, but this time with a twist. So it'll be more fun than you can possibly imagine. All right, have a good weekend, everyone. I'll talk to you soon.